partial derivatives. Now let's just take a look at this definition below here. It says let f of xy be a function of two variables. Then the partial derivatives of f with respect to x, written as df dx over dx, or fx, f sub x, is defined as df over dx equals the limit of f of x plus h, comma y, minus f of xy over h. And that is the limit of that as h goes to 0. Now, when we think of this definition, we should think of the definition when we first learned derivative. It too was a limit definition, and it is. And in general, that's where we start at with these derivatives. And we did back then, and then we found an easy way to do them, right? We had the power rules and all those other things. So that's what we're going to deal with here with these partial derivatives. We're going to talk about all of that. But first, let's talk about this limit definition and run through it. Because again, we'll do the harder one first, then appreciate the quick one. So that's in general how we do it. Now the second one, take a look at this. This is the partial derivative of f with respect to y now. This is new to us because now we're in multivariable calculus. And this says written as df over dy, or f little y, is defined as df over dy equals the limit as k goes to 0 of f, and that's just an x there, but look at this, y plus k minus f of xy over k. So now what we're seeing here is, now we're extending it. Now think about this when we talk about horizontal shifts with functions. They always use that x minus h kind of scenario, didn't they? And the same thing with k. K was always referred to as our vertical shift up and down. So I liked how they kept the consistency with the variables here. But what we're going to do is we're going to actually just take the partial derivatives here. And if you look below, it says calculate the partial derivatives dz dx using the limit definition. Z equals x squared minus 3xy plus y squared. So we're only going to find dz dx here. So another way to write that is f of x, or f sub x. I don't really know how to say that. I usually just say fx. So that's fine. So now if we're going to set this up, this is actually going to be the limit as h goes to 0. I actually kind of want to do both of these. I think that would be fun to do the dz dx and then the dz dy. Or we should just do the dz dy, but we'll do the dz dx. All right, and you'll see how that all kind of works together here. So now the first thing is we need to find this one here. And that says f of x plus h comma y. So this is telling me that I'm going to plug in x plus h in for x and leave y alone because y is just y sitting there. So that's all I'm going to do here. So I'm just going to plug in x plus h in for x. And we've done that before. This is just now multivariable. But it doesn't really add anything more to it other than that variable sitting there. Minus 3, and then I have an x plus h again, comma y. And then I have plus y squared. Now this piece I just wrote, that's just this piece here. That's what that is down there. Now what we're going to do is we're going to have to do the minus fxy. So now I have a minus, and I always use a parenthesis after this because there's always these signs changing when it's more than one term, and this one is 3 terms. So this is going to be a minus x squared, 3xy plus y squared. So then that'll all be over h. So then that's going to equal the limit as h goes to 0. And all I'm going to do here is simplify this by multiplying everything through and distributive property and all that stuff. And we're going to end up with x squared plus 2xh plus h squared. And then this is going to be minus 3xy minus, and then just multiplying this here. And that's where that came from. And then now I'm going to multiply it times the h. So that's going to be minus 3yh. And then plus y squared. That's here. And then now for this piece, I'm just going to distribute that negative through. So that's going to be negative x squared plus 3 xy minus y squared. And that's still all over h. And then just notice what cancels here. So I have this positive x squared, negative x squared. Positive 3xy, negative 3xy. Positive y squared, negative y squared. So then we end up with, the limit as h goes to 0 of 2xh plus h squared minus 3yh all over h. Now what I'm going to do is I'm going to factor an h out of the top, because that's all I can do with the top is factor an h out. So that equals the limit as h goes to 0 of, and if I factor that h out, that's going to be 2x plus h minus 3y all over h. And then those h's are going to cancel. And I have the limit as h goes to 0 of 2x plus h minus 3y. And then the limit as h goes to 0, that's my only h there. So I'm going to end up with 2x minus 3y. So that's the answer for this one here. That's the partial derivative. Now think of it this way. If I was just going to do zx, now again, I can use this notation here. And I should have here, but I was saying here essentially that my f of xy equals z, and that's why I use the fx notation. In my mind, that's what I did. But I'm really dealing with zx here, same thing. And if I think about the partial derivatives here with respect to x, I have an x here and I have an x there. So this is going to be 0. So that would mean then that would be 2x, right? Because that's just a power rule. And the y is just a constant, remember that. So that would be minus 3y. And look at the answer that we came up with. It's the same. But again, you'll have problems on the test that are, I got to do the limit definition here. And then there'll be problems where I can just do it simply, just by taking the power rules and the stuff I already know. So for now, I just kind of wanted to show you that there. But this is our answer for this one here.